Hello, welcome to this lesson of our study of complex analysis. Okay, so in this lesson we just go through some examples of what you call harmonic functions. Okay, so I believe that after these three, this one and this and that examples, I know you would definitely, or you'll be able to understand what we call the harmonic functions better. Okay, so we just go through the examples. Okay, so show that the following functions are harmonic and find their harmonic conjugates. Okay, so with respect to this, what you can do here is that you just look at it and think about it. How do I solve this question? Okay, so I have a hint in the next page which says that to solve this, you need use the Laplace equation together with the CR equations. Okay, so we use the Laplace equation to show that the Laplace equation is the first one. Okay, that is this one. Okay, this one here, which is del u, the squared u del s squared plus the squared u del y squared equals 0, meaning the second partial derivative of the function given with respect to the individual variables. When you sum them, that is the second order partial derivative of the function. When you sum them, you get 0, and that is when you get 0, it means that the function is actually harmonic. Then you come and use the CR equation, that is the Cauchy-Reimann equation, to solve for the harmonic conjugate. Okay, so it's a 2-in-1 work here. All right, so let's move on to the first one. Okay, so the first question is s squared minus y squared. So since in our Laplace equation we named the function u, here we can actually let u be equal to s squared. Okay, let me write it well. S squared minus y squared. Okay, now with this, to show that this is Laplace, this is harmonic, we have to make sure that it satisfies the Laplace equation, and we have to find the second order partial derivative of u with respect to the individual variables. So del squared u del s squared is what we need, but first of all you find del u del x first. Okay, and that will give us 2x, and then del squared u del s squared is actually equal to 2. Then you go to the second one, which is del u del y, which is equal to minus 2y. Then you go to del squared u del y squared. Okay, and that is equal to negative 2. Now let's sum this, the second partial, this one and this one, and see. So the squared u del s squared is 2 plus del squared u del y squared is negative 2, and that is actually equal to 0. Okay, 0 equals 0. So this means that the Laplace equation is being satisfied for this particular function. That is the first question. Hence, this function u, which is equal to this function u here, we've named it u, is actually harmonic. Okay, now if it is harmonic, we let v be the harmonic conjugate of u. Okay, let me write it well for you. Let v be the harmonic conjugate. Okay, so let me shorten it with HC, harmonic conjugate, okay, of u. Then we can say that a function f which is equal to u, which was a function we just said, plus iv will be analytic. Okay, so if this is indeed analytic, then we can use the CR equations to generate differential equations involving v, and then we use it to solve v. Okay, so then from the CR equation we know our u is equal to what? S squared minus y squared. So what we need is our v. Okay, but from the CR equations we can say that del u del x from the Cauchy-Reimann equation, okay, is always equal to del v del y if this is analytic. And indeed, when v is the harmonic conjugate of u, then it means that this whole thing will be analytic. That is, the whole f here, this whole f will be analytic, and then it will satisfy the CR equations, okay? And then also del u del y will be equal to negative del v del x. Now we know that del u del x was giving us 2x, and then we are saying this is equal to del v del y, okay? Okay, so I hope this is true. That is 2x equals that, and you can rearrange this equation and say that del v del y is actually equal to 2x, which gives us our first differential equation. Let's call that equation 1. Okay, and so with the other one, which is del u del y equals minus del v del x, will tell us that del u del y was negative 2y, then it's supposed to be equal to minus del v del x. Okay, so in cancellation and rearranging equation, you have del v del x here being equals to 2y, and this is equation 2. Okay, so we pick these two differential equations and solve them. Alright, so let's go to the next page. So we know that del v del y is equal to, from the first equation, we know that it's equal to 2x. Okay, now if that is the case, rearranging, we have del v is equal to 2x del y. Okay, now with this, we integrate both sides with respect to their individual variables. So the right side or the left side, integrate it with respect to v, and you get v is equal to, you integrate the left side with respect to, or the right side with respect to y, and you get 2xy plus some constants, and this constant should be h of x, because the function v is depending on, we see it to be dependent on both x and y, and here we are integrating this side. We integrated this side with respect to y, because of the dy there, and because of that, you have to leave our constant in terms of a function of x. Okay, so now with this you could see that we have to look for h of x before you can actually find our total v. Okay, so let's call this an equation, what's equation 3? Okay, and try to differentiate this v with respect to x again and see this v that we've gotten in equation 3. So we'll get del v del x is equal to 2y, okay, plus h prime of x, because h of x is a function of x, so when you differentiate you get h prime of x. And then let's call this also equation 4. So, but we know that from equation 2, you can go to the previous page and check. From equation 2, I mean this one. Okay, let me use a different color for you. From this equation, okay, here, you can see that del v del x is actually equal to 2y. So you just go ahead and wherever you see del v del x, you put 2y there. Okay, so you get 2y is equal to 2y plus h prime of x, and this will result into taking 2y to the other side and keeping h prime of x. You get 0. 2y minus 2y, so you get 0 equals h prime of x. And this, let me use a different color here, and this will get h prime of x here is equal to 0. So h prime of x means what? dy dh dx. Okay, and we are saying that this is equal to 0. So we have dh is equal to 0 dx. Please don't write 0, and try to integrate both sides. So I integrate h with respect to h, I will get h, which will be in terms of h of x. Or you can still maintain it or write it as h of x, or you can just leave it as h. Okay, and it's equal to the integral of 0 dx. So integral of 0 is a constant. Okay, c. So it means that our h of x here that we want to look for is actually equal to c. So therefore, we just come back and put h of x, which is c, in the v, and we'll get our v. So we know that here v is equal to 2xy plus some h of x, but we've been able to find h of x, which says that h of x or h is actually a constant. So we have v being equal to 2x y plus a constant, and this is actually the harmonic conjugate of u. Okay, so in case where the constant c is 0, then we'll have v to be equal to 2x minus 2xy. Okay, so you can go ahead and check if this function v together with u being equal to, what was u, s squared minus y squared, you can check these and see if this is analytic together with this saying that f is equal to u plus iv. You definitely come back to a conclusion that this is actually analytic. Okay, so that is our v, that is our harmonic conjugate to this function s squared minus y squared. So let's move on to the next one, which is a bit more difficult because of the sign and the sign in it, the hyperbolic functions in it. Okay, so with this one, the second one, you're supposed to show that this is harmonic, and then also find its harmonic conjugate. Okay, so we let the same way we let u be equal to sine x sine y. Okay, so we find del u del x, and that is equal to cosh, because when you differentiate the whole of this with respect to x, the sine y does not have any, it doesn't have any x in it, so you have to differentiate only the sine aspect, this one, which has the x. Okay, and so when you differentiate sine s with respect to s, you get cos s. Okay, then you keep your constant. This time the sine y become a constant. Okay, then you continue to the squared u del s squared will then also be equal to, there is no x in the sine y, so we just concentrate on the cos x. So when you differentiate cos s with respect to s, you still get when you differentiate cos s with respect to x, you get minus sine s. Okay, I hope this is cool. Oh, sorry, you get cos sine s. Okay, sorry, you still get, when it comes to the hyperbolic function, it doesn't change. You still get sine s, it doesn't change any sign. Okay, I'm really sorry for that. Sine y. Okay, so you get sine s sine y. That's the second derivative of u with respect to x. Now you go ahead and find that of del u del y, and that is equal to, you differentiate the whole of this with respect to y. The sine aspect has no y in it, so I just differentiate the sine y and I'll get cos y. So I have sine x cos y. Okay, so I'll go ahead and find this del squared u del y squared, and this will give me, when I differentiate cos y, I will get negative, so I'll get minus sine s sine y. When you differentiate cos y, you get negative sine y, so that will affect everything there. So if I'm to sum these two, okay, if I'm to sum these two, this one and this one, okay, when I sum them and I get 0, then it means the function is harmonic. So indeed, you can go ahead and sum it yourself, or I'll just go through that with you. So del squared u del s squared plus del squared u, so I have del squared u del s squared plus del squared u del y squared. Okay, that's what we are coming to do. Now the squared u del s squared is what, this one. Okay, so when you sum it, you get sine x sine y, okay, plus negative this, so you become minus sine x sine y, and this will give me 0. Okay, this whole result will give me 0. When you subtract them or when you add them, you get 0. So because of the addition resulting into 0, then it means that this function u, which is the sine x sine y, is actually harmonic. So our next task here is to find a harmonic conjugate. Okay, now to find a harmonic conjugate, like I said, you let some function v be the harmonic conjugate of u, and you know your u already. Your u is what, equal to sine x sine y. Okay, now if v is harmonic conjugate to u, then it means that if we let a function f be equal to u plus iv, then this function will be analytic. Okay, I mean, this u is what we have here, so our problem here, or our task here, is to find v. Now from the CR equation, when a function is analytic, what do? You say that if you have an analytic function, then del u del x should be equal to del v del y. Okay, from the CR equations. Now, which means that del v del y will be equal to what? So we go ahead and check the answer we had for del u del x, or you can still differentiate it with respect to x, and that gave us cos x sine y. Okay, now the next one is del u del y should be equal to negative del v del x. So it means that minus of del v del x will be equal to del u del y, and that was sine x cos y. Okay, I hope you get this. I mean, just represent your del u del y there, and that was sine x cos y. Okay, so let's go to the next page and then do it proper there. We have, first of all, del v del y, okay, is equal to cos s sine y. Okay, so I have cos s, let me write it well for you. Okay, cos s sine y. So let's name this equation 1, and we have negative del v. So in effect, I can still cancel things out. Okay, so I can divide through by negative 1, and then I'll get the negative to be on the other side. I mean this equation. Okay, so I'll have del v del x here being equal to negative sine x cos y. Okay, and this is equation 2. Now we are supposed to solve this differential equation. So the solution to this differential equation, let's first of all solve for the first one. Okay, because that will make us feel comfortable, because this is with respect to y, and the y is just in the sine y, it's not in the sine. Okay, so let's go ahead and use the first one. So with the first one, rearranging, I have del v equals cos. Okay, I have del v equals cos x sine y dy. Okay, I just rearranged it. Now if I integrate both sides of the equation with their respective variables, I have here v being equal to, when I integrate sine y, because cos s here is just a constant, so I integrate sine y with respect to y, I'll get negative cos y. Okay, so I have minus cos x cos y plus some constant, which is h of x. Okay, so like we did for the first one, you go ahead and differentiate this new equation, let's call it equation 3, with respect to x again. So del v del x here will give us, when I differentiate everything with respect to x, I have only cos s here, so when I differentiate, I'll get minus sine x cos y. Okay, here is actually cos y. Let me erase that for you. This one, I mean, it's supposed to be cos y. Okay, then plus h prime of x here. Okay, so we go ahead and find del v del x is actually given in equation 2, so we come and put it here, I mean this side of the equation. Okay, put it at this side of the equation. Let's call this 4. I hope you understand. So you put it there, you have minus sin, okay, minus sin x cos y is equal to negative sin s cos y plus h prime of x. Okay, now you can send this one to the other side. Okay, so we have minus sin s cos y plus sin s cos y, and it's equal to h prime of x. So I'll have 0 equals h prime of x. In effect, it's the same as h prime of x equals 0. And like I did for the other one, the h, the x, okay, it's actually the h dx, that's the h prime of x, is equal to 0, which implies that the h is equal to 0 dx. And now when I integrate both, I have h equals c, a constant. Okay, so h prime of x is actually a constant as well. So you go back to your equation and find wherever you see h prime of x, I mean this one, the equation 3. Let me use a red pen to underline it for you. Where we have v, this one, v equals minus cos s cos y plus h prime of x. You just go back to that one and put your h of x, actually you put your h of s back there, okay, and that will be your harmonic conjugate. So we have v equals minus cos x cos s cos y plus our h of s, and h of s was a constant c. So this is actually the harmonic conjugate to, or the harmonic conjugate of the function u. Okay, so it's the harmonic conjugate of u, which is equal to, u was given us what? So you can go ahead and then find your u, which is sin x sin y. Okay, sin x sin y. Okay, and together v and u together will give us an analytic function. So in case where c is just 0, then we have only this part. Okay, all right, so let's move on to the next one. This is the last question for this lesson. Okay, so with this, for us to know that if it is harmonic or not, we just have to let our u be equal to xy plus 3s squared y minus y squared. Okay, so with this, we just find del u, del x, and it's equal to y, okay, plus 6xy. Okay, now del squared u, del s squared is equal to 6y. So you go to del u, del y, okay, and that is equal to x plus 3s squared minus 2y. Okay, then move on to the next one, which is the del squared u, del y squared, and that is equal to minus 2. Now you can see clearly here that after the second partial derivative, okay, of u, the summation of 6y, which is the del squared u, del s squared, and the second one, which is the del squared u, del y squared, would never be equal to 0, since we still have some y in it. Okay, this is not equal to 0. Hence it means that this function here, this one is not harmonic. Okay, it's not harmonic. So once it's not harmonic, we are done. Okay, I hope you understood everything that we went through. Kindly, I would advise you go through integrations and differentiations if you really want to get every question under analytic and harmonic functions correct, because you end up doing differential equations using integration and stuff. Okay, so just try to revise on your integration and your differentiation, and as well as your differential equations as well. Okay, all right, so Thank you, and don't forget to subscribe to my channel. All right, see you next time.